All right, now we're going to start talking about the surface area of our parametric surfaces. So let's define surface area for our general parametric surface. Think about our rectangle in UV space right here. So we have a nice little sub-rectangle right there who has a length of delta U and delta V, length and width. You'll notice that at our bottom corner, we're using that as some U sub I star and V sub J star. And that is our R sub ijth area. For instance, we've talked about things like this before, if you remember. That is going to correspond through our vector function R to what we're going to end up calling a patch on our parametric surface right there. It certainly does not have to be a rectangle as it kind of looks in UV space. So maybe this reminds you of parallelograms. We are mapping small rectangular regions in UV space to small parallelograms. So I'll draw a parallelogram right there. That was a bad parallelogram, my bad. In X, Y, Z space, these small parallelograms we're going to call patches. It's not technically a parallelogram. We're approximating our patch with a parallelogram. Think about looking at the tangent plane to the surface, really, really close to that point that we're doing it at. And while the surface might bend out of that tangent plane, it should be close enough that we're going to look at that tangent plane and it's going to look like a parallelogram. So that's going to help us find some of these areas. Back up here at my sketch of my parallelogram, these are going to be, to find the area, of one of these small parallelograms, we need to know the tangent vectors forming the sides of the parallelogram, which would be R sub U star and R sub V star, but those are going to be scaled by our change of U and our change of V. So what we really have is this over here is delta U, R sub U star, and then we have delta V and R sub V star. And if you recall from earlier in the year, how are we going to find the area of a parallelogram? We can take the magnitude of the cross product of these two vectors. So, there we go. Fit it in. Look at me go. And this can be actually rewritten. I'm not going to show you how or why. You're welcome to take the actual cross product of something like this to figure it out if you'd like. But this can actually be rewritten. It's supposed to be a V, sorry about that. As the magnitude of R sub U star times R sub V, or not times cross product with R sub V star times delta U delta V. And as with all of these things that we've been doing where we are determining where these formulas come from, we start sending some of these things to be infinity or being infinitely small. So our areas, when we add up all these little patches to get the approximation of the surface area of our parametric surface, is a double summation of R sub U star cross magnitude of R sub U star cross R sub V star times delta U delta V, where, as we send these approximations, as the distances get smaller and smaller and we make as many patches as we can heading to infinity, taking limits and such, you will notice that it's going to look like our double integral of the magnitude of R sub U cross R sub V du dv. So we'll go to our definition. If a smooth parametric surface S is given by our vector valued function R of two variables U and V, where U and V are in some domain D, and S is covered just once by the UV ranges, as UV ranges throughout the parameter of domain D. So we don't want things like covering up itself. So we don't want like a cylinder where you're like putting wrapping paper around it over and over and over again. We just want to cover it once. Then the surface area of that parameterized surface is given by this double integral right here. Double integral over that region D of the magnitude of R sub U cross R sub V dA, where R sub U and R sub V are those partial derivatives of R with respect to U and V, respectively. So got to know that formula right there. That is going to give you your surface area. So let's look at an example. Find the exact surface area of the portion of the spiral ramp given by the function R defined as U cosine V, U sine V, and V, where U and V are bounded by those given things right there. So U is bounded by 0 and 1, and V is bounded by 0 and U. So we have this thing right here. We're trying to find the surface area for this. So here we go. What is this going to look like? You need our vector R sub U, which is going to be cosine V, sine V, and 0. We need our vector R sub V, which is going to be negative U, sine of V, U cosine V, and 1. We're going to need the cross product, R sub U cross R sub V. So we're going to draw our little matrix here. So we could take our determinant, cosine V, sine V, 0, negative U, sine V. I should have written the bottom row first. Whatever, it's fine. And that cross product is going to be, looks like we have sine minus 0, sine of V minus 0. Shouldn't just skip saying those. We're going to have 0 minus cosine of V. So we're going to have a negative cosine of V. And then we're going to have, I should not have written this right here. Let's write this underneath, my bad. Sine of V, negative cosine of V. And then we're going to have cosine of V times U cosine of V, which is U, oh, come on, pen, U cosine squared of V minus, and we're going to have negative U sine V times sine of V, so that's going to be plus U sine squared of V, which I'm sure we're all well aware that we can rewrite that as just U. Now, we need the magnitude. So we're going to take the magnitude of that vector right there, which is going to be the square root of sine of V squared plus negative cosine of V squared plus U squared, which I think you will all be okay with me writing that as the square root of 1 plus U squared. So to find the area of that part of the surface corresponding to that domain given, we are going to do the double integral over D, the square root of 1 plus U squared dA, which is going to be equal to integral 0 to 1, integral 0 to U of 1 plus U squared dV du. Taking the integral with respect to V, it's just going to put a V into the integrand. We're going to plug in U and 0. That is going to give us our integral 0 to 1 of U square root of 1 plus U squared du. You can do some U substitution here. Maybe we shouldn't call it U substitution. Maybe you call it alpha substitution. Letting alpha equal 1 plus U squared. So d alpha equals 2U du, which we know is going to give us, sorry about that, our substitution factor of a half. Taking the integral of the square root of alpha is going to give us 2/3 times 1 plus U squared to the 3/2, and then we need to plug in 1 and 0. So that is 1/3 times, plugging in 1, we get 2 to the 3/2, minus, when we plug in 0, we get 1 to the 3/2, that's just 1. Really can't write that a whole lot better. Maybe you want to do 1/3 times the quantity 2 root 2 minus 1, but whatever. Doesn't look all that much better now, does it? All right, example 3. We'll do one more for this video. I think I have just enough time to fit this one in before this cuts off, and then I'll have a very short video for the last page. So let's consider a special case where z is a function of x and y. We're going to find the formula for the surface area of S over D. So we're going to use the trivial parameterization for this one. Trivial, I can spell. The trivial parameterization for this is going to be r of xy, which is x comma y comma, I guess we're just going to call this f of xy because that's what z is equal to. So we need our two partial derivatives here. So derivative of r with respect to x is going to give us 1, 0, and then our partial of f with respect to x, and then our r sub y is going to be 0, 1, and then partial of f with respect to y, excuse me. Taking the cross product of this, I will note right here that this is something that if you want to memorize, you can, because this pops up frequently enough where if you just want to memorize the setup for this, you don't have to write the determinant over and over again. That is going to be 0 minus the partial of f with respect to x. And then our middle component is going to be 0 minus the partial of f with respect to y. And then our last component is going to be 1 minus 0. So that is our normal vector in terms, oh, that's bad, in terms of x and y. That one right there, you're welcome to remember how to get that. That might save you a little bit of time doing cross products. We need the magnitude if we're coming up with the surface area. So we're going to take the magnitude of that, which is going to give us the square root of s sub x squared plus f sub y squared plus 1. The negatives will cancel with squaring. So you might notice if we write our surface area formula, that is going to be the double integral over d, square root of 1 plus del f del x squared plus del f del y squared dA. You remember this from earlier in the year 15.5. We saw this formula before for the surface area of our surface in xy space. So we are showing right here that this is a very specific case of the general parametric surface area equation that formula that we now know. If our parametric surface is just defined in terms of x and y, that's why this double integral gives us the surface area. Okay, I'm going to create a short video for the last page here because I'm running out of time before it kicks me out. You can join me for that last one if you need.